In the cargo hold of a military-grade freighter, surrounded by tension cables and shock sensors, stands something most logistics engineers never trained for: a giraffe, towering at 5.5 meters. With a spine as delicate as a suspension bridge and a cardiovascular system built to defy gravity, the giraffe is not merely an animal in transit. It is a biomechanical anomaly. Every transport operation involving one of these animals becomes a test of engineering sensitivity, biological insight, and extreme precision. It's not just about getting from A to B. It's about maintaining a vertical equilibrium so complex, even a few degrees of tilt can collapse the system from within. From a distance, giraffes look calm, even serene. But inside, their bodies operate under constant physiological tension. Their heart must pump blood vertically over 2 meters just to keep the brain awake. A minor shift during transport, an uncalculated tilt, a sudden deceleration, all can unbalance this natural hydraulic tower. What makes the challenge more daunting is the silence of the failure. No loud alarms, no visible distress. Just a drop in cerebral pressure and a sudden, irreversible collapse. To move a giraffe is to engage in high-stakes vascular management with a column of blood suspended inside a narrow neck that cannot afford a mistake. Logistics teams treat giraffes not as livestock, but as biological towers, structurally rigid at a glance, but internally fragile. That's why the equipment designed to transport them borrows more from aerospace engineering than from ranching. One such crate system includes gyroscopic stabilization bars, capable of adjusting in real time to external vibrations. Visually, it's closer to a vertical rocket transport rig than anything seen in traditional animal handling. It's not about protection from the outside. It's about internal alignment, pressure distribution, and zero-impact suspension. To understand why this matters, consider a submarine periscope. In naval operations, it must rise, lock, and remain vertically stabilized. Any lateral motion affects visibility, calibration, and structural integrity. Now imagine that periscope is alive, breathing, and highly stress-reactive. That's the giraffe in a crate. And like a periscope, its height is both its asset and its greatest risk. Without vertical dampening and low-angle tilting thresholds, movement becomes not only disorienting but physiologically dangerous. The true technical trigger, the point where all planning converges, is the carotid artery. This narrow, high-pressure vessel runs like a column of water from heart to brain, and its management during transport is non-negotiable. Misalignment can trigger cerebral edema in minutes. That's why even before the giraffe steps into the crate, engineers are already thinking like vascular architects. They're not just moving an animal. They're moving a system in vertical suspension with pressure thresholds, biological torque, and collapse margins thinner than those in industrial hydraulics. This is the invisible engineering that few people ever hear about. A logistics ballet where time, physics, and biology must align perfectly to transport one of Earth's most structurally complex creatures across oceans, borders, and ecosystems. And it begins with a single crate designed not for comfort, but for vascular survival. In the confined silence of a cargo aircraft, where airflow is measured in cubic feet per second and every shift in cabin pressure is monitored, a new variable emerged: heat. Not heat from engines or sun exposure, but from within the crate itself, a thermal trap formed by poor ventilation and excessive insulation. Giraffes, despite their desert lineage, are vulnerable to internal heat accumulation, and inside a transport crate, stress and confinement can push their internal temperature beyond safe margins in minutes. The result is often invisible, until it's too late. Beneath their spotted hide, giraffes regulate heat inefficiently. Their long necks, designed to access the high canopy, also expose them to uneven thermal gradients. During air transport, particularly in under-ventilated crates, the animal enters a feedback loop of stress, shallow breathing, and rising internal acidity. Without movement, without warning, this stress builds until metabolic systems fail. In some operations, this silent process has led to muscle collapse and respiratory arrest, all within 90 seconds. To confront this, engineers turn to an unlikely source of inspiration: vertical mushroom farms. These controlled environments require exact airflow patterns: slow, uniform, and minimally turbulent. Applying the same principle, modular crate systems now use laminar airflow channels, distributed vertically, to keep the giraffe's entire body in a state of thermal balance. It's not about air conditioning, it's about controlled dispersion, engineered to mimic the open breeze of the savanna while suspended inside a steel fuselage. Stakes are physiological. In high-stress transport scenarios, giraffes have shown blood lactate levels comparable to thoroughbred horses at full gallop, despite standing completely still. This lactate surge doesn't come from effort, but from panic, from confinement, from the metabolic cost of being vertical in a box that behaves more like a thermal chamber than an open plain. It's a shock response, triggered by internal chemistry, not external action, and it's measurable, which means it can be prevented. In 2021, a giraffe relocation effort in Namibia revealed the fragile line between protection and risk. The animal had been given extra padding around the neck support, a decision meant to prevent muscular fatigue. But that padding, not designed for thermal dissipation, caused a temperature spike of 3.4 degrees Celsius in less than an hour. The giraffe collapsed at the edge of the tarmac just minutes before loading. No alarm was triggered, no equipment had failed, but the crate, in trying to protect, had become a heat trap. That's why modern giraffe transport strategy embraces a radical principle. The crate must behave like an open savanna, not like a cocoon, not like a padded chamber. It must breathe, it must flow, it must mirror the thermal openness of the wild while managing the mechanical necessities of airlift. Because the threat isn't noise, it isn't turbulence, it's silence. The silent rise in temperature, the silent drop in pressure, the silent consequences of treating a giraffe like a generic live cargo load. This is not just a matter of care, it's a matter of engineering discipline. Behind every successful relocation is a blueprint of airflow vectors, pressure zones, and biological limits applied not to machines, but to an animal that stands like a tower and crashes like a system. And it begins, not at altitude, but in the crate's design. The giraffe's neck is not just an anatomical marvel, it is a suspended, pressurized column, vulnerable to forces most cargo systems are not designed to detect. At over 2 meters in length, supported by a lattice of delicate vertebrae and vascular pressure differentials, the neck becomes the critical axis of risk during any movement. And the danger lies not in speed or noise, but in angle, a factor so subtle that its consequences are often recorded only after the incident has passed. What breaks the system is not always the jolt, it's the sway. In mechanical terms, the giraffe's neck behaves like a vertical hydraulic line under tension. Rapid, angular shifts, especially those that happen without warning during loading or in-flight turbulence, can induce micro-tears in venous valves, disturb arterial rhythm, or cause transient ischemic episodes, a kind of internal blackout. These aren't injuries you can see, but they are felt. And in the narrow balance of vascular flow, they can cascade into complete collapse. To anticipate and avoid these failures, modern giraffe transport operations incorporate biomechanical simulations, a method borrowed directly from the testing protocols of hydraulic cylinders and excavators. Just as heavy equipment engineers model how a piston reacts under sudden load torque, giraffe crate designers simulate how neck tissues respond to tilt vectors during acceleration, deceleration, and even crane-based elevation. Every shift is plotted, every force mapped. It is a choreography of physics around a living reactive system. What these simulations revealed was unexpected. Giraffes transported in wider crates, once considered more comfortable, exhibited higher levels of agitation. With too much space, they attempted to self-correct their balance with micro-movements, constant, energy-draining adjustments that triggered a measurable increase in heart rate variability and muscular fatigue. It was a paradox. More space meant more instability. The solution was a V-shaped padded enclosure, which gently pressed against the animal's flanks, preventing side sway and stabilizing the cervical axis. In effect, stillness was achieved through confinement, not openness. There are records of what happens when that stability is lost. In one operation in South Africa, a male giraffe was being loaded via crane when the crate experienced a 7-degree lateral swing, imperceptible in real time, but later traced through internal accelerometer data. Within minutes, the giraffe exhibited signs of neural shock, loss of balance, muscle rigidity, and lowered neck tension. The operation was aborted. No hardware had failed, but the data told the story. The animal had experienced a hydraulic-style failure, not from trauma, but from accumulated stress. That's why in the latest generation of transport crates, tilt sensors are embedded directly into the structural frame. These sensors, calibrated to react to shifts under 2 degrees, now interface with warning systems that can freeze motion, recalibrate suspension, or signal for immediate stabilization. It is no longer acceptable to treat crate loading as a static event. It is a dynamic process, with live data guiding every second. The principle is as simple as it is vital. If your crate ignores dynamic tilt vectors, you're not transporting a giraffe, you're risking spinal failure in motion. And that risk doesn't come from ignorance. It comes from underestimating what vertical fragility really means. Because to move a giraffe is not to move an animal. It is to move a column of biological tension through a 3-dimensional field of mechanical risks. And every degree counts. Transporting a giraffe is not a logistical challenge. It's a redefinition of what logistics must become. In a world where speed, volume, and efficiency dominate the conversation, the giraffe imposes a different order of complexity. It is tall, but it is not about height. It is sensitive, but it is not about fragility. The giraffe stands at the intersection of biology and mechanics, forcing engineers to solve a puzzle where the pieces are living tissue, fluctuating pressure, and motion that can't afford to be imprecise. Crate design becomes more than structural containment. It becomes a question of how to preserve life through controlled motion and how to engineer stillness without forcing it. To move a giraffe is to simulate a vertical vascular system, one that is stretched, reactive, and constantly fighting gravity. Its heart pumps against a 2-meter column of blood to keep the brain alive. Its neck isn't simply long. It is a channel of forces held in fragile balance. During transport, each tilt, each sway, each acceleration introduces risks that are usually irrelevant in the world of live cargo. A giraffe's physiology does not tolerate instability the way other animals do. It requires an environment where equilibrium is not just maintained, it is actively managed. That's where technology steps in. Advanced crate systems are now equipped with multi-axis tilt sensors, vibration compensators, airflow actuators, and real-time biofeedback interfaces. This isn't luxury, it's necessity. The Giraffe Safe platform in Kenya exemplifies this evolution by integrating telemetry, pulse oximetry, environmental monitors, and mechanical response protocols. It transforms a crate into a mobile, biomechanical environment. The system adjusts airflow based on stress levels. It fine-tunes suspension response based on cervical angle. It reacts to the giraffe, not as cargo, but as a constantly changing biological signal. It's a shift in mindset. The crate is no longer seen as a passive structure, but as an adaptive tool, something that listens, calculates, and intervenes. And to design such a tool, engineers must leave behind the paradigms of traditional transport. They must think like vascular designers, like neurological guardians. They must treat the crate as a bridge between worlds, mechanical and organic, static and alive. The analogy is not just metaphorical. Think of the articulated sprayer booms used in precision agriculture. These systems adjust in real time to the undulations of terrain, maintaining optimal nozzle height to preserve crop integrity. In giraffe transport, the objective is similar: dynamic response to shifting external variables, with an eye always fixed on internal stability. Controlled sway, measured torque, harmonized pressure. These crates are not cages, they are instruments. And in this orchestration, the giraffe becomes a benchmark, not because it is exotic, but because it is demanding. And in that demand, it reveals the limitations of our current systems. It shows where we must evolve toward smarter logistics, toward deeper integration of biology and engineering, toward a future where moving life requires more than force. It requires comprehension. What began as a crate for a tall animal becomes a new standard for what it means to move life safely. The giraffe doesn't just challenge our tools, it rewrites the expectations we place on them. It is not just about moving from place to place. It is about carrying a system intact, through air, through space, through time, with every heartbeat accounted for and every degree of tilt held in balance.